Hey guys, welcome to part 3 of fluid dynamics. If you haven't yet watched parts 1 and 2, I highly recommend you go back and do that. At the end of part 2, I asked you to go back to the FET simulation and to complete a sort of investigation to see how changing the pipe height from one end to the other would or could affect the changes in pressure in the pipe, and then to try to add a term to the conservation of energy equation that we established at the end of the last video. So if you haven't done that yet or had a chance to play with the simulation, go ahead and try that and then come back to the video and we'll get started. So just to do a quick recall, we talked about looking at two different positions within the pipe. And we said if we compared both positions, the total amount of energy of the fluid had to be the same. So we had written out a kinetic energy term, which was 1/2 rho velocity squared. And remember, rho now was the substitute in for mass because the volume canceled out in every term. Now we also saw that there was a pressure term that we could add there that had to do with the amount of work done by the fluid. And so if you don't know what I'm talking about right now, go back to video 2 and take a look at that. Now at the other location in the pipe, we also saw that I would have a rho v squared term and a pressure term. So in other words, we said that this constant total amount of energy would be the same at both locations, but where the velocity was higher, the pressure would be lower and vice versa. Now we've added in a change in height. So if we take a little snapshot here from the simulation, we see that the pipe has had a change in height from the left to the right side. So what we can do then is think about what kind of term would we add to a conservation of energy equation. So go ahead and pause the video and try to see what you would insert into the conservation of energy equation for each side. So hopefully you were able to put in a gravitational potential energy component, or you could say the work done by gravity. And we know that for a general case is m times g, the force times the displacement h. And in this case, remember, for each term we substituted in rho times volume, so density times volume for the mass. And then because volume canceled out in every term, it would also have to cancel out in this term, right? So we'd be left with rho times g times h. Now, remember, h height is already a vertical displacement. So I'm going to take this out, and because I'm dealing with the difference between two places, I'm going to actually write a separate term on each side and have it as rho times g times y1, in other words, the vertical position at the, say, the left-hand side. And then I'm going to add in rho times g times y2 on the right-hand side, and that would be that horizontal position. Now, what I could do if I wanted to write it as height is I could leave all my other terms the same, so 1/2 rho v squared plus p1, and now you're going to see what I do on the other side, equals 1/2 rho v squared plus p2 plus, and then we'd have this combined term, rho times g times y2 minus y1, which is also known as height. So you can see there's two different ways that you could write it, but both of them mean the same thing. So if we take a look at this first case scenario over here, we can see that the total amount of energy that the fluid has within the system has to be split up between three things, right? Velocity, pressure, and then also a height or a change in position, vertical position. And so that becomes very important when determining how much energy there is. Now, in the next video, although it's not a content-based video, I'm going to work 2 or 3 practice problems. So we'll use this equation and kind of take a look at it. But what's most important to recognize here, as we've said before in the previous video, is that this is a statement of conservation of energy. And really what it's doing is it's showing that there's three different kinds of energy or work being accounted for in this fluid, and how if we compare one place to another, we can actually find relationships between fluid velocity, fluid pressure, fluid height, and so on and so forth. So what I want to focus on here next are some of the really cool applications that use this, we could say, equation or law, and this is known as Bernoulli's equation, and it was sort of attributed to Daniel Bernoulli, and he actually was a physicist mathematician that came up with so many different aspects of mathematical physics that we use today. But one of the very cool applications, and there's several that this relationship in this equation shows, one of the cool ones is a natural ventilation system. So if you've been to, I think it's usually tropical places where the temperature, there's not really a need for central heating because it never gets too cold. And although it does get kind of warm, there's usually on islands, there's a strong breeze that comes through. So if we have a structure sort of like this where we have walls and then the roof is set up like this, there's usually some open space on either side, right over here and here, and it's covered with netting. And this netting allows the air to blow through across the top of the house or stall or whatever you want to call it. Now, if we think about what's going to happen is when huge gusts of wind blow across the top of this structure, there is a very high fluid velocity. Now, according to the Bernoulli function, 1/2 rho v squared plus rho gy plus p, we're going to see here that when I have a high speed in my fluid, the pressure is low. And so it creates a low pressure place up here at the top, and down here at the bottom of the house where most people would be residing, what's going to happen is relative to the top there, the pressure down here is going to be pretty high, and that's going to cause the airflow to move up, because remember we said fluid will always flow from a place of high pressure to a place of low pressure. And we've established that many times in this fluid dynamics series. So basically what's happening is you can either think of it as the fluid being sucked up to the roof or the fluid being pushed up to the roof, right? And so it creates this really nice natural ventilation and kind of moves a lot of the stale air that would be down here at the bottom up to the top. And it's all because of the pressure difference, right? And the pressure difference is established by the velocity difference. So up here we have a high velocity. Of course, down here, because there's walls on either side, we really don't have a velocity at all, right? Or it's very low compared to at the top. And so there'd be quite a big pressure difference. This leads very succinctly into another example where this occurs, and this would be in gale force winds or tornadoes, where you have a house and you'll go through a neighborhood, and we're not talking here about the tornado actually physically knocking into homes, because of course it would destroy the whole home, but actually wind blowing above the roof of the house. So you can think about up here above the roof, the winds are blowing very fast. So I have this high fluid velocity and therefore a very low pressure. Now on the inside of the house, because everything's boarded up, the velocity is basically zero. So there's an extremely high pressure inside the home compared to outside, and the house will actually push its own roof off. So roofs get blown off during a storm, not because the wind is physically necessarily pushing the roof off, but because of the pressure difference that's created. It actually kind of causes a net force or net pressure pushing up, which will blow the roof off the house. Now the foundation of the two examples that I just showed is actually this Venturi tube, and it's named after the physicist and scientist who discovered this effect. And basically what we have here is a pipe whose diameter is changing, which we've had many examples of so far. The only difference here is that we have a little vertical section of pipe in each of the areas where the pipe diameter has changed. Now these vertical sections of pipe are open to the atmosphere, and we're going to say that we fill this fluid completely through the pipe, and then we push the fluid through this bottom horizontal section. Now what I'd like you to do is pause the video and talk yourself through ranking the fluid velocity and the fluid pressure at each of the three locations that are lettered A, B, and C. So over here, this one, it has the widest area, so therefore it must have the smallest velocity, and because it has the smallest velocity, it should have the highest pressure. We then step to this one, which has the medium area, therefore the second velocity or second lowest velocity, and therefore the second highest pressure. And then we have the most restricted section of the pipe, which would have the smallest area, therefore the highest velocity, and therefore the lowest pressure. So now if we take the ideas about the pressures as we've ranked them, we can now take our next attempt at ranking the heights of the fluid in each of the vertical tubes. So think about it, they're all open to the atmosphere. So they're all experiencing the same downward pressure from the atmosphere. Which one would have the highest and which one would have the lowest fluid height in the vertical tube? So hopefully you can see that the one that has the greatest fluid pressure at that point would push the fluid itself, because it would have the greatest difference in pressure, and it would cause the fluid to be pushed up that tube. And then of course the one that has the greatest speed passing through it, and therefore the lowest pressure, will have the lowest pressure height. So the heights in the tubes would be different. Now I'm going to leave you with a challenge, and this one is a little bit more involved than the ones that I usually leave you with, but it's very interesting and very cool. There is a device on an airplane, most modern aircraft, that is called a pitot tube, spelled P-I-T-O-T. And the pitot tube works in this basic way, like the Venturi tube. And it's used, it's a crucial instrument on a plane, especially for autopilot, but very specifically it's used to determine the airflow speed around the plane so that the pilots can make good judgments. Now in 2009, Air France Flight 447 sadly crashed into the Atlantic. It disappeared from Rio de Janeiro and it was flying to Europe, and all of a sudden it basically fell out of the sky. Now it took a while for them to find the black boxes and a lot of the information, but the investigators were able to piece together what had happened, and it has something to do with the pitot tubes, which is very interesting. So I'm going to offer a link here to try to access this amazing Nova PBS documentary on the crash of Flight 447. And I highly recommend watching this documentary and then doing some investigating yourself to find out if the team of engineers that Nova put together before the actual black box and final results were found, to see how close they were in their analysis of what had gone wrong and caused the flight to crash. Because they used a lot of the material that we just talked about with fluid dynamics, and they were able to come up with a sort of a possible series of events. It's very cool, and I highly recommend you watch it. Other than that, the next video will be just some practice problems to help you out.